Having completed all the variations of flip-flops, the flip-flops, various types of flip-flops, the T flip-flop, the JK, the D flip-flop, and control of the flip-flops, the timing and everything. So we have to know everything. So let's do one example here, okay? Let's just start with an example, and the example we are doing is nothing new. Remember, we actually started with a counter. And when we put the latches together, we said that the latches, if you want to do a counter, we put an incrementer, and then we found that that doesn't work. And so what we did was we put JK or I'm sorry, we put master slave flip flops, and then we showed that yes, that does work. And so I'm gonna do another flip, another counter, but to make it different from the previous one, what I'm doing is I'm making it a counter that only counts to 4, from 0 to 4. That means it is a modulo 5 counter. A modulo 5 counter means that it's a circuit that has 5 different counts. Okay. And then I will start with that and then start adding a few things to it. All right. So I'm designing a modulo 5 counter. The initial state of it is 0, goes up to 4, and then goes back to the initial value of 0, 0, 0. And so that's a counter, and it is a modulo 5 counter. Okay. Because it is modulo 5 counter, it requires 3 bits, 3 flip-flops. Okay, 3 flip-flops. I'm going to be doing this with the simplest flip-flop, the D flip-flop. Okay. The initial state is 0, 0, 0. My circuit has a clock and a reset. Okay. The reset is asynchronous. Async. And the clock is obviously the clock, which can use rising edge clock. Okay, that is not in the definition of the problem. The definition of the problem says this is a counter, and then at the end, when you use a flip-flop with the positive edge flip-flop, this definition becomes rising edge counter. Okay, so what I'm saying now is you don't really have to worry about the type of flip-flop that you're using at this point. And so the counter has 3 outputs. I'm using 3 flip-flops, and Q2, Q1, Q0. They come directly from flip-flop outputs. Okay, so that's the definition of my problem. Let's get a little bit more inside the counter and show the behavior of the counter with the transition table. Okay, remember I've shown you transition table for the D flip-flop, right? The D flip-flop transition table is this. If you have Q plus, okay, what happens is if your D is, let's do this, if your D is 0 or 1, your Q plus becomes 0 or 1. What it means is Q plus is D. What it means is what you put on D becomes your next state later. This is the characteristic equation for the D flip-flop. That's why I'm saying is the simplest. The whatever you put on the D input, clock it, goes on the output. Here I have 3 flip-flops, and this is how I want the 3 flip-flops to work. It is a counter. So I start with 0, 0, 0. My next state, that means after I clock it, becomes 0, 0, 1. So the number 0 becomes 1. 0, 0, 1, I clock it, becomes 2. That's the second one. 0, 1, 0, I clock it, becomes 3. 3, I clock it, becomes 4. 4, I clock it, rolls back over to 0, 0, 0. Okay, and then clock it again, becomes 1, and so on. So that's what I was showing here, that when it becomes 1, 0, 0, the next one is just repeating the same sequence. What happens to these values? I'm not worried about those, and I'm hoping I never get those values. Okay, I will make some corrections for that. Some provisions for that as well. Okay, and this is called a transition table. What it says is the following. If the present state of the 3 flip-flops is, for example, 0, 1, 0, and I clock it, it makes a transition to 0, 1, 1. That's all. That's all it's saying. If it's 0, 1, 1, I clock it, becomes 1, 0, 0. This transition table doesn't say anything about the type of flip-flops I'm going to use to build it. But since this is our first example, I use a flip-flop that is easy to implement, and that's the D flip-flop. And it turns out that this D flip-flop, even though it's the simplest flip-flop, it is the most popular, the most common flip-flop as well. And also, this D flip-flop is one that most of the CAD tools, design automation tools, use D flip-flops. Okay? And if you look at the programmable logic devices, also they have D flip-flops as the main default flip-flop. And if you want to have other flip-flops, in most cases, you have to build those out of D flip-flop. So D flip-flop is a good choice. That's all I'm saying here. All right, so this is my transition, and then I say, well, transition means that if I have something, the output, then the output of the flip-flop, then I clock it, the output becomes the next state. All right, how do I implement this? What I have to turn this into is something I'm familiar with, which is kernel map or truth table. What I say is, if I decide that I want to use D flip-flop, what I want as the next state of my flip-flop is what goes on the D input of my flip-flop at this time. See, Q plus is D. What it means is, if you want 0, 1, 1 on the output, after the clock, put 0, 1, 1 on the D inputs, and then clock it, that becomes your output. As simple as that, right? What it means is, if you want to make this transition table, the table on the left, put these same values on the D inputs, and then you are guaranteed that after the clock, these inputs become your next outputs. Okay? That's not necessarily the case for other flip-flops. For D flip-flops, it is. So what I say is this. Transition table is a little bit difficult for me to deal with because that's not like a truth table. It has timing in it. But then this table on the right-hand side that decides on the values of D, that doesn't have timing, and it looks exactly like a truth table. It defines the combinational part of my circuit. It defines, based on Q2, Q1, Q0, what I want for D2, D1, D0. So what I have here is a truth table for 3 outputs, D1, D2, D1, and D0. Okay? So that looks like any truth table. So let's go and build this. I just turn that truth table to this these 3 kernel maps. Look, for example, 0, 1, 1, present 0, 1, 1, D2, D1, D0 becomes 1, 0, 0. 0, 1, 1 becomes 1, 0, 0. 1, 0, 0 becomes 0, 0, 0. That's a rollover. Okay? How about the other 3 cases? I don't really care. My counter should never be in these states anyway. So let's do the mapping. And for D2, this is the easy map. This becomes Q1, Q0. For D1, these two become Q1, Q0 exclusive OR. And for D0, this becomes this, okay, which is Q2 bar, Q0 bar. This is really Q2, Q0 OR together. Okay, that means the NOR of the two. So what it means is I need an AND for this, I need an XOR for this, I need a NOR for implementation of D0. This becomes my circuit. Okay? So I built D2, D1, and D0 using Q2, Q1, Q0 as inputs. That's the combinational part. But remember what I said. I said what you put on D2, D1, D0 inputs of the 3 flip-flops, of the 3D flip-flops, whatever you put there, you clock it, that becomes your Q plus. So with this, I have achieved this transition table and I have achieved this counter. I have built my counter. And this is exactly my counter. My counter has a clock, which I never talked about. Now that I put the flip-flops here, I talk about the clock. It is rising edge? Yes, it is rising edge. Okay? It has an asynchronous reset. Okay? It is asynchronous active high reset. Did I ever talk about this? No, I did not. Okay, they don't participate in the design of my circuit, in the functional description of my circuit. They only participate in the operation, and that has to do with the type of flip-flop that you use. If you want to be complete, this is C1, this is C1, those are 1D, this is the reset, this is the reset, and this is the reset. Okay? And my counter is working and counting from 000 to 001. And if I ever want to reset it asynchronously, this is how I do it. All right, so this is the circuit I have. Let's add some controls to this circuit. Okay. What I want to do is I want to add an enable to my circuit. Okay, so I don't want it to count every time clock ticks. I don't want it to count. I want to decide sometime I want to count, sometime I don't want to count. And these are the flip-flops that I have. So what do? I put an enable in the flip-flops. Remember what I said about enable. I said about enable that the enable inputs, if the flip-flop has the enable, you can use it. If it doesn't have, you have to add an enable using an external enable using a multiplexer. So this is the choice I have. I have to add 3 multiplexers on the way of D going into the flip-flops, and then I have this enable input that comes in controls this. So if enable is 1, D2 clocks in. If enable is 1, D1 clocks in. If enable is 1, D0 clocks in. Okay? And if enable is 0, Q2 goes back to Q1. This and this. Okay? What did I do? I just added an enable input. Therefore, my counter only counts when enable is 1. Let's go back to the diagram here and also add an enable input. Okay, this is an active high enable input for this circuit. An enable active high. All right, what else do I want to do? Let's add an initialization input. Okay, let's say, for example, remember that I already have a reset, but then what if I wanted to start it in 000 synchronously? Okay, so this is what, so this is adding enable. Now I want to add initialization. Add initialization. Okay. If I want to add 000, I put 3 AND gates in there. If I want to add, for example, if I want to initialize it to 100, I put an OR gate and 2 AND gates. Okay. Let's say that I like to initialize this. Anytime I decide I want to initialize it to 0, 1, 0. Okay, initialize to 0, 1, 0. Why that? I just want to show you the hardware. Okay, so the hardware becomes as such. Okay, I added for those that I want to set to 0, I added an AND gate, and for the outputs that I want to set to 1, initialize to 1, I put an OR gate. This becomes my init signal. Okay, that init signal complemented goes into this AND gate. Complemented goes into this AND gate. And then just take that init signal, put it into the OR gate. Now let's see what I have added. If my init is 1, then the OR gate has a 1 there. The 2 AND gates have zeros on the outputs, and therefore, as soon as I clock, 0, 1, 0 goes into the counter of my circuit, and the counter starts from that value. So let's go back to the diagram, original diagram, and add the init signal as well, which initializes my counter to 0, 1, 0. All right. What else can I do with this counter? See, the counter starts with 0, 0, 0, goes to 0, 1, 0, and 0, 1, 1, and 0, 0. No, it goes from 0, 0, 0 to 0, 0, 1, and then to 1, 0, 0, and then goes back. Okay. So while enabled, provided I have the enable, while enabled, as I'm clocking it, it just goes through this. That means every 5 clock cycle, it goes back to the 0, 0, 0 state. Okay. What if I just take this output and look at that output to see what happens? See, what happens is this. 1, 2, 3, 4. When clock becomes 1, that output Q2 is still 0. This is count 0, 0, 1. Then it becomes 0, 1, 0. Then it becomes 0, 1, 1. Then it becomes 1, 0, 0. Okay, 1, 0, 0. And then finally, with the next count, it becomes 0, 0, 0 again. Look at my Q output. My Q output becomes 1 on this edge of the clock and then back to 0. Okay, Q2 output, Q2 output. What is happening is for every 5 clock edges, or for every 5 clock pulses, I get a pulse on the output. Okay, so I can call this whole circuit, taking the Q2 output as the circuit output, a divide by 5 circuit. Okay, so that's something. We did a circuit and we added enable, and so if we go back to the original circuit, this output can also be regarded as divide by 5 frequency wise. All right, we are done with the example. We are done with the flip-flops, and we have covered all kinds of flip-flops, and next will be, let's do some real circuits.